We continue an example of what we studied last time. An example is this. I am given three functions, e to the x, sine x, and cosine x, and I want to verify that these functions form a fundamental set of solutions for the ODE shown in here. So the answer then involves two steps. Step number one, verify that y1, y2, y3, that they all solve, let's label this star, that they all solve this equation. So to verify, I would need to compute up to the third derivative of each function. So y1 is e to the x, and then if I take derivatives of e to the x, they're all still e to the x. So in this case, all derivatives up to the third one are all e to the x. And now we substitute these derivatives into the equation. So then we have that y triple prime, y1 triple prime minus y1 double prime plus y1 prime minus y1 is going to be e to the x minus e to the x plus e to the x minus e to the x. Of course, all e to the x is cancelled, so we get 0, and so therefore y1 solves equation star. Let's look at y2. y2 is sine x. Again, I will need three derivatives. y2 prime is cosine x. y2 double prime is minus sine x. y2 triple prime is minus cosine of x. Now substitute y2 triple prime minus y2 double prime plus y2 prime minus y2. Triple prime is minus cosine of x. Minus y2 double prime is minus sine of x. Plus y2 prime is cosine of x. And then minus y2, which is sine x. So cosine x cancel out. Sine x and minus sine x cancel out. You get 0. So therefore y2 solves the equation star. And now let's repeat this for y3. So y3 is cosine of x. y3 prime is minus sine x. y3 double prime is then minus cosine of x. And y3 triple prime is sine x. So now we substitute that into the equation. So the left-hand side of the equation is like this, except that 2 should be replaced by 3. And if they do so, then y3 triple prime is sine x minus y3 prime is minus cosine of x plus y3 prime, that's minus sine x, and minus y3 minus cosine of x. Sine and minus sine cancel, plus cosine and minus cosine cancel, so cosine is also a solution of this equation. So y3 solves star as well. So all three functions in this case are solutions of the ODE, and I just need to verify in order for them to form a fundamental set of solution. The second step is to verify that y1, y2, y3 are linearly independent. And that I can do by computing the Wronskian. So I need W of y1, y2, y3. In this case, I have three functions, so I have to have 3 by 3 determinant. So the first column is going to be y1. Let me write this down. y1, y1 prime, y1 double prime, y2, y2 prime, y2 double prime, and then y3, y3 prime, y3 double prime. Okay, y1 is e to the x, y2 is sine x, y3 is cosine of x. So derivatives of e to the x are e to the x. First derivative of sine is cosine of x. Second derivative is minus sine x. Then derivative of cosine minus sine x. And derivative of that, second derivative is minus cosine of x. Okay, so this is a determinant that we have to compute. So it is going to be e to the x times the determinant of cosine x minus sine x minus sine x minus cosine of x. And then the second element in the first row is sine x, because it's an element with indices 1, 2. Total is odd number, so minus sine x times the determinant of a matrix that remains that if I remove the second column in the first row. So that would be e to the x minus sine x minus cosine of x. And then finally, the element in the third position in the first row is cosine of x, so it would be plus cosine x times the determinant you get by crossing out the first row and the last column. So e to the x cosine x minus sine x. And so now we're ready to compute the determinant. So we have e to the x, then cosine x times minus cosine of x minus cosine square of x minus product of minus sine with itself. Minus sine times minus sine is sine square, because it's a secondary diagonal. I'm going to subtract this number, so minus sine square of x. Then the second determinant, minus sine x, and determinant itself is going to be minus cosine x e to the x plus sine x e to the x, because I'm taking a product of these two things minus a product of those two things. Okay, and lastly, plus cosine of x, and then this 2 by 2 determinant is minus e to the x sine x minus e to the x cosine of x. So that's the 2 by 2 determinant times cosine of x. And let's see if all of this can be simplified. If you look carefully at this expression, you see that there is a factor of e to the x everywhere. And then we look first at this parenthesis, minus cosine square minus sine square. That's minus sine square plus cosine square. So the thing that I have in parentheses is just minus 1. All right, and then we have minus sine x times this difference. So that should be plus sine x cosine x minus sine square root of x for the first parenthesis. And for the second, I have two products, one like this, and one is like that. So minus e to the x I've taken out, so minus sine x cosine of x, and then minus cosine square root of x. And now I see that sine x, cosine x I can cancel out. And minus sine square minus cosine square is minus 1. There's already 1 minus 1 in the parentheses, in the brackets. So what we get is minus 2 e to the x. So the Vronsky, in my case, is not equal to 0 because exponential can never be equal to 0. And so therefore, y1, y2, y3 are linearly independent. And so we're done because we verified what we were asked to verify. Okay, so the last item that I want to cover here is going to be this, and I'm going to illustrate it using second order equations. So we're going to talk about non-homogeneous linear ODEs of higher order. And so we're using the example which is of second order, but this example should apply to linear ODEs of any order. Okay, so I'm going to consider the equation A2 of x y double prime plus A1 of x y prime plus A0 of x y equal to 0. And also a corresponding non-homogeneous equation, which will look exactly the same, except that on the right, I'm going to put the function f of x. Let's label this equation as 1, and this equation as 2. All right, so let's suppose that the function yh satisfies equation 1, and yp satisfies equation 2. And the question is, what can we say about y equal to yp plus yh. Am I going to get anything but value about this equation? And let's try to insert this function into the left-hand side of equation 2, which also is the left-hand side of equation 1. So a2 of x, yp plus yh double prime plus a1 of x, yp plus yh prime plus a0 of yp plus yh. I want to understand if I can equate this to anything. Well, so in this case, because taking derivatives is a linear operation, derivative of yp plus yh is derivative of yp plus derivative of yh, like y is a second derivative. So I can rewrite my expression as follows. I can get rid of derivatives outside of the parentheses, and I can replace them on functions inside. Right, this doesn't change anything because, again, taking derivative is a linear operation. Okay, but then multiplication is also linear, so I can write this as a2, as usual, I'm going to quit writing x, a0 as a function of x2. So I'm going to get a2 yp double prime plus a2 yh double prime plus a1 yp prime plus a1 yh prime plus a0 yp plus a0 yh. All right, and so now what I'm going to do, I'm going to collect terms with yp together and terms with yh together. So a2 yp double prime, yes, plus a1 yp prime plus a0 yp, that's the first parenthesis, plus a2 yh double prime plus a1 yh prime plus a0 yh. Okay, but then I know that yp satisfies equation 2. So if I plug in yp into the equation 2, then the right-hand side is going to be equal to f of x. But plugging yp into the equation 2 is precisely the same thing as what I'm computing here, right? Because it's a2 yp double prime plus a1 yp prime plus a0 yp. So that means that this parenthesis is actually nothing but this, which is equal to that. So this is equal to f of x. And likewise, the expression over here is the same as the expression on the left of the homogeneous equation, of which I know yh is a solution. So that means that this parenthesis is still going to be equal to 0. And so when I add all of these things together, I get f of x. So what did we figure out? That this computation must be equal to f of x. And therefore, yp plus yh is a solution of the non-homogeneous equation 2, right? Because the right-hand side is equal to f. And so the conclusion from this is the following. Adding any homogeneous solution or rather, let me rephrase this. Adding any solution of 1 to a solution of 2 produces a solution of 2. Okay, so any solution of a non-homogeneous equation, or a solution of a non-homogeneous equation, can be obtained by taking another solution of a non-homogeneous equation and adding a solution of a corresponding homogeneous equation to it. So this is called, again, a superposition principle. But now for non-homogeneous ODE. Okay? And now because YH is a solution, is any solution of 1, then as YH we can use the general solution of the equation of a homogeneous equation 1. All right, so if in this case I'm dealing with second order equations, that means that the general solution of the second order homogeneous equation, linear, is going to be the one that contains 2 unknown constants. So therefore, as YH, I can use a general solution of 1 in the form y equal to C1 y1 plus C2 y2. And so then how do I get my solution of a non-homogeneous equation? It will look like, so y equal to yp plus C1 y1 plus C2 y2. This solves the equation, non-homogeneous equation 2, and it contains two unknowns. C1 and C2. And if I'm solving a generic second-order equation, then remember that that generic equation second-order equation should have a general solution that involves two unknown constants. So what I have done here, I was able to produce the solution, the general solution of my non-homogeneous equation, because what I got is an equation which contains two unknown constants. So more generally in the future, not right now, but in the future, when we'll be solving non-homogeneous equations, the general solution always is going to be some particular solution of a non-homogeneous equation plus the general solution of the homogeneous equation. All right.